Question number 8. The given statement P of n is 1 into 2 plus 2 into 2 square plus 3 into 2 cube plus etc. The nth term is n into 2 power n, and that is equal to n minus 1 into 2 power n plus 1 and plus 2. So let us first prove that P of 1 is true. P of 1 will have only the first term equal to, now 1 minus 1 is 0, the first term becomes 0 plus 2. So 2 equals 2. Therefore, P of 1 statement is true. Then let P of k be true. That is, we assume that P of k statement is true. And the statement is 1 into 2 plus 2 into 2 square plus 3 into 2 cube, etc. Kth term is k times 2 power k equals, substitute n as k minus 1, 2 power k plus 1 and plus 2. Now let us write P of k statement. That is the result to be proved. P of k plus 1. 1 into 2 plus 2 into 2 square, etc. Kth term is k into 2 power k, and k plus 1th term will be k plus 1 times 2 power k plus 1 equal to, now in this right hand side of P of n, we will substitute n as k plus 1. So k plus 1 minus 1 becomes k. 2 power k plus 1 is k plus 2 and plus 2. Now on the left hand side of P of k plus 1, we can use the result of P of k. So total of first k terms is this, which is k minus 1 times 2 power k plus 1 plus 2 and then the last term, which is the k plus 1th term. Now here 2 power k plus 1 term is common. We get k minus 1 from the first term and k plus 1 from the third term. 1 gets cancelled and we have plus 2. So it becomes 2 times k times 2 power k plus 1. 2 power 1 and 2 power k plus 1. Therefore, the answer becomes k times 2 power k plus 1 will become k plus 2 and plus 2. And this is the right hand side of the result which we have to prove, P of k plus 1 result. Now let's write the conclusion step. Therefore, P of k plus 1 is true whenever P of k is true. Because using P of k only, we have proved that P of k plus 1 is true. Therefore, the given statement P of n is true for all natural numbers n. Question 9. P of n statement is 1 by 2 plus 1 by 4 plus 1 by 8, etc. The nth term is 1 by 2 power n, and this summation is 1 minus 1 by 2 power n. P of 1 statement. Here the left hand side has n terms, but P of 1 will have only one term, which is half. On the other side, n is 1. Half, 1 minus half is also half. Therefore, P of 1 is true. Now let P of k be true. P of k statement is half plus 1 by 4 plus 1 by 8, etc. Kth term is 1 by 2 power k equals 1 minus 1 by 2 power k. Now to prove, we have to prove P of k plus 1 statement. Now P of k plus 1 statement is half plus 1 by 4 plus 1 by 8 plus etc. Kth term is 1 by 2 power k, and we have to write the last term, which is k plus 1th term, 1 by 2 power k plus 1 equal to 1 minus 1 by 2 power n has to be substituted as k plus 1. This is the result to be proved. Now, as usual, for the first k terms, we will write the result using P of k. Therefore, the left hand side of this P of k plus 1 statement becomes, I am writing the total of first k terms from here, and plus k plus 1th term, this term I am writing. Now 1 minus, I am taking minus sign out, so this will become minus, because minus of minus gives you plus sign. Now I am going to combine these two terms by taking LCM. Here LCM is 2 power k plus 1, because 2 power k plus 1 is 2 power k into 2. So 2 power k factor is already present in this. So no need to take LCM as 2 power k into 2 power k plus 1. Now this is into 2 minus 1, which is 1 minus 1 by 2 raised to k plus 1, and this is our right hand side to be proved. We got the answer. Therefore, P of k plus 1 is true whenever P of k is true. Therefore, P of n is true for all n belonging to capital N. Let's do question number 10. So the given statement P of n is 1 by 2 into 5. It is not 2.5, it is 2 into 5. Similarly, 1 divided by, it is not 5.8, it is 5 into 8. And the third term is 1 by 8 times 11 plus etc. The nth term is 1 divided by 3n minus 1 times 3n plus 2 equal to n by 6n plus 4. This is the right hand side. The first term equal to, plug in the value of n as 1, 6 plus 4. This is 1 by 10, that is also 1 by 10. Therefore, P of 1 is true. Now let P of k be true. Now P of k statement is 1 by 2 into 5, 1 by 5 into 8, plus etc. Kth term I am writing 3k minus 1 into 3k plus 2 equal to k divided by 6k plus 4. Now the result to be proved. P of k plus 1 statement. 1 by 2 into 5 plus 1 by 5 into 8, etc. Kth term is 3k minus 1 by 3k minus 1 times 3k plus 2, and we have to write k plus 1th term. The denominator is 3n minus 1, 3n plus 2. Now replace n by k plus 1 and check. What do we get? Here also k plus 1. If you simplify, this is 3k plus 3 minus 1, which gives you plus 2. And here 3k, 3 plus 2. 3 plus 2 is 5. This is our k plus 1th term. So 1 by 3k plus 2 times 3k plus 5 equal to, here on the right hand side of P of n, put n as k plus 1. So k plus 1 divided by 6n plus 4, where n is k plus 1. Let us write the simplified answer here. 6k, 6 into 1 is 6, 6 plus 4, 10. Perfect. Okay, now let us prove this. For the first k terms, we can use P of k result. Therefore, the left hand side of this equation becomes, by P of k, this total is k by 6k plus 4, and write k plus 1th term, which is 1 by 3k plus 2 into 3k plus 5. This factor can be simplified as 2 times 3k plus 2. First we will take the common factor out. So we have k by 2 and 1 by 3k plus 5. Now let us take LCM. Here the LCM is 1 by 3k plus 2. The LCM here is 2 times 3k plus 5. So it is k into this 3k square plus 5k, and 1 into 2 is 2. So we need to factorize the numerator. I'll do the factorization here. 3k square plus 5k and plus 2. Product is 6. Sum is 5. So I'm splitting the middle term as 3k and 2k. Total is 5k and product also 6k square we get. From the first two terms, 3k is common. And from the last two terms, 2 is common. Therefore, the factors are k plus 1 is one factor, 3k plus 2 is the other factor. So 1 upon 3k plus 2, and I'm writing the factors here, k plus 1 and 3k plus 2. That's what we got by factorization. 2 times 3k plus 5 is the denominator. Now we can cancel this common factor. This is equal to k plus 1 divided by, if I open the brackets of the denominator, I get 6k plus 10, and this is the right hand side of P of k plus 1 result. Therefore, let us write the conclusion steps. P of k plus 1 is true whenever P of k is true. Therefore, P of n is true. for all small n belonging to capital N. Question number 11. The statement P of n is 1 by 1 into 2 into 3 plus 1 by 2 into 3 into 4 plus 1 by 3 into 4 into 5, etc. The nth term is 1 by n into n plus 1 into n plus 2. This is equal to n into n plus 3 divided by 4 times n plus 1 times n plus 2. Let us do the first step of proving P of 1 true. So P of 1 will have only the first term, only one term it will have on the left hand side, because it is a series given, the left hand side. Now substitute n as 1 here. We get 1 by 6 equals 1 by 6. Therefore P of 1 is true. Now we assume that P of k is true. Let's write P of k statement, which is 1 divided by 1 into 2 into 3 plus 1 divided by 2 into 3 into 4, etc. Kth term is 1 by k times k plus 1 times k plus 2. And this is equal to k into k plus 3 divided by 4 into k plus 1 into k plus 2. P of k plus 1 statement we are going to prove, which is 1 by 1 into 2 into 3 plus 1 by 2 into 3 into 4, etc. I am writing the kth term, and then let us write k plus 1th term. To write k plus 1th term, in this last term of P of n, I have to write n as k plus 1. So n is k plus 1. K plus 1 plus 1, the next factor, k plus 2, and k plus 1 plus 2 will become k plus 3. Now to write the right hand side, we will substitute n as k plus 1 here, k plus 1, k plus 1 plus 3 will become k plus 4 divided by 4 times n plus 1. n is k plus 1. So k plus 1 plus 1. Again n is k plus 1. K plus 1 plus 2 gives you k plus 3. This is the result which we have to prove. So the first k terms total is this, we know. So let us take the left hand side of P of k plus 1 statement. So LHS is the total for the first k terms is this. And now let us add k plus 1th term, which is 1 divided by k plus 1 into k plus 2 into k plus 3. Take out the common factors. We have k plus 1 and k plus 2 common in the denominator. We have k square plus 3k by 4 from the first term and 1 by k plus 3 from the second term. Here let us take LCM. The LCM is 4 times k plus 3. So we need to multiply k square plus 3k and k plus 3. Let us distribute k cube, 3k square, 3k square and 9k plus 1 into 4 is 4. Let us simplify this. k plus 1 into k plus 2. Here let us add the like terms. 3k square plus 3k square is 6k square plus 9k plus 4. Now look at the answer to be proved. The answer is k plus 1 into k plus 4 divided by 4 times k plus 2 into k plus 3. So this k plus 1 is not there in the denominator. That means k plus 1 must be a factor of this numerator term. So let us factorize the numerator. So we know for sure that k plus 1 is going to be the factor of the numerator. So I am going to divide the numerator by k plus 1. K square into k cube plus 1 into k square. Change the sign. These two are getting cancelled. 6 minus 1, 5k square, and bring down the next term. Now I have to write 5 here, 5k here. 5k into k is 5k square and 1 into 5k. Change the sign. 9 minus 5 is 4k, and bring down the next term, plus 4. 4 times it goes, we get 4k plus 4. Change the sign, both are getting cancelled and the remainder is 0. Therefore, we get 1 by k plus 1 into k plus 2. Now the numerator can be written as k plus 1 is one factor. The other factor is the quotient, which is k square plus 5k plus 4. If you multiply these two factors, you get back that k cube plus 6k square. This expression we get. Divided by 4 times k plus 3. Now k plus 1 could be cancelled, and I can further factorize this k square plus 5k plus 4. The factors are k plus 1 and k plus 4. That's it. The denominator is 4 times k plus 2 into k plus 3, and this is the right hand side of the result to be proved. Therefore, p of k plus 1 is true. Whenever p of k is true. Therefore, the given result is true for all natural numbers. Question 12. This is P of n statement, which is a plus ar plus ar square, etc. ar power n minus 1, and this is equal to a times r power n minus 1 divided by r minus 1. This is GP, geometric progression. Now P of 1 will have only the first term, a, which is equal to a into, we have to substitute n as 1. So r power 1 minus 1 by r minus 1. We get a equals a. Therefore, P of 1 result is true. Let P of k be true. This is our induction step. And P of k statement is a, ar, ar square, etc. ar power k minus 1 is equal to a times r power k minus 1 divided by r minus 1. Now to prove P of k plus 1 statement, that is ar square, etc. Kth term is ar power k minus 1 and k plus 1th term is ar power k plus 1 minus 1. Look at the power of r here in the P of n statement. So replace n by k plus 1, which becomes r power k, equal to, now replace n by k plus 1 here, which will become r power k plus 1 minus 1 divided by r minus 1. Now the first k terms total we know, which is the right hand side of P of k statement. Okay, therefore left hand side of this equation is equal to, I am replacing the first k terms total by this, and this is k plus 1th term. Simplification is easy. We will first take a out, and then take LCM. LCM is r minus 1. We get r power k minus 1 plus, we have to multiply. R into r power k is r power k plus 1 and minus 1 into r power k. These two terms are getting cancelled. A times r power k plus 1 minus 1 divided by r minus 1. Therefore, P of k plus 1 is true whenever P of k is true. Therefore, P of n is true for all n belonging to capital N. Question 13. The statement is 1 plus 3 by 1, and here we have multiplication in between the terms, into 1 plus 5 by 4. In other questions we had plus sum of n terms we had. Here product of n terms. Third term is 1 plus 7 by 9, etc. 1 plus 2n plus 1 by n square equal to n plus 1 the whole square. This is the given statement. Let us do P of 1. We'll have only the first term, the left hand side, and the right hand side is 1 plus 1, 2 square, so 4 equals 4. Therefore P of 1 is true. Next, let P of k be true and write P of k statement. One plus 3 by 1, here we have product of k terms. 1 plus 5 by 4 into kth term I am writing 1 plus 2k plus 1 by k square, and this total, this product is equal to k plus 1 the whole square. Now to prove P of k plus 1 statement, here we will have product of k plus 1 terms. So 1 plus 1, 3 by 1 into 1 plus 5 by 4 into the third term 1 plus 7 by 9, etc. Kth term is 1 plus 2k plus 1 by k square, and we have to write k plus 1th term. Nth term in P of n statement is this. So substitute n as k plus 1. One plus, if I open these brackets, we get 2k plus 2 plus 1, which becomes 3, divided by k plus 1 the whole square. And this is equal to, n is k plus 1, so k plus 1 plus 1, which is k plus 2 the whole square. This is what we have to prove. Now product of k terms we know from P of k result. So by P of k, product of first k terms is k plus 1 the whole square into k plus 1th term is this. Simplification is so simple in this case. Let's take k plus 1 the whole square as LCM. We get k plus 1 the whole square. I am expanding and writing k square 2k plus 1. And here the numerator is 2k plus 3. So plus 2k plus 3 it becomes. Denominators are getting cancelled. We get k square plus 4k plus 4. And this is the expansion of k plus 2 the whole square, and we got the right hand side. Therefore, P of k plus 1 is true whenever P of k is true. Therefore, P of n is true for all n belonging to capital N. The next question, 14th question, is also similar type. Here also we have product of n terms. Let us write the given statement P of n. 1 plus 1 by n multiplied by 1 plus 1 by 2, then 1 plus 1 by 3. Nth term is 1 plus 1 by n, and this product is equal to n plus 1. So P of 1 will have only the first term, and that is equal to 1 plus 1, so 2 is equal to 2. Therefore P of 1 statement is true. Now induction step, let P of k be true. And this statement is product of k terms I have to take, and that is equal to k plus 1. Now to prove P of k plus 1, here I have to write product of k plus 1 terms. So 1 plus 1 by 1, 1 plus 1 by 2, kth term is 1 plus 1 by k, and k plus 1th term will be 1 plus 1 by k plus 1, equal to k plus 1 becomes k plus 2. This is the result to be proved. So product of the first k terms we know. From P of k result, we can replace it by this k plus 1, and the last term k plus 1th term should be multiplied with. This simplification is so easy to do. Just take LCM. We get k plus 1 plus 1, which is k plus 2. And that is the right hand side of P of k plus 1 statement. Therefore, P of k plus 1 is true whenever P of k is true. Therefore, P of n is true for all n belonging to capital N. Question 15. P of n statement is 1 square, 3 square, 5 square, etc. plus 2n minus 1 the whole square equal to n into 2n minus 1 into 2n plus 1 divided by 3. Let us do P of 1 step, which will have only the first term on the left hand side. Here put n as 1, 2 minus 1 is 1, 2 plus 1 is 3, by 3 we get 1 equal to 1. Therefore, P of 1 result is true. Now let P of k be true. And the result is, P of k result is 1 square plus 3 square plus 5 square, etc. 2k minus 1 the whole square equal to, substitute n as k into 2k minus 1 into 2k plus 1 divided by 3. Now to prove, we are going to prove P of k plus 1 result. And the result is 1 square plus 3 square plus 5 square, and kth term is 2k minus 1 the whole square. And see the nth term, this is the nth term. Now substitute n as k plus 1 to find k plus 1th term, which is 2k. This is 2 minus 1. 2 minus 1 is plus 1 and the whole square. Similarly, on the left hand side, substitute n as k plus 1. And the next factor is 2n minus 1. 2n minus 1 just now we did, 2k plus 1 it becomes. Then we have 2n plus 1. So replace n as k plus 1. We get 2k plus 3. This is 2 plus 1 makes it 3 divided by 3. This is the result to be proved. Again, the sum of first k terms we know. By P of k, sum of the first k terms is k into 2k minus 1 into 2k plus 1 divided by 3. And this k plus 1th term should be added to it. Take out the common factor. 2k plus 1 is common. And we have the other two factors. I am multiplying, divided by 3 and plus 2k plus 1. Because we have 2k plus 1 the whole square, one of the factors we took it out, the other factor remains. 2k plus 1, take LCM 3, it is 2k square minus k, we have to multiply by 3, 6k plus 3. 2k plus 1 minus k plus 6k. Add these two terms, we get 5k divided by 3. Let us factorize and write. Product is 2 3s are 6 and sum should be 5. So let us split the middle term as 2k and 3k. 2 3s are 6 and total is 5. From the first two terms 2k is common, and from the last two terms 3 is common. Two k plus 1. K plus 1 is a common factor, take it out. The other factor is 2k plus 3. Now this is the right hand side. Therefore, P of k plus 1 is true. Whenever P of k is true. Therefore, P of n is true for all n belonging to capital N.
Thanks for watching and please subscribe the channel.